Thank you very much, Hans. And let me also welcome you at today's webinar. And I hope you will have a good 1 hour with us. So next slide, please, Hans. Here you can see content of first part of today's webinar. After short introduction, we will have a look at the wastewater heat recovery system, principles, how it works, and efficiency. At current market situation in Europe, then we will have a look at the decarbonisation potential of this solution. First at the single household level, then we will go to EU 28 level, and we will have a look at a certain scenario of WWHR and how this system can contribute to energy savings targets of the renovation wave. And after additional benefits, we will look at policy recognition and recommendations for these systems. Next slide, please. So I think that most of you is well aware of the fact that 40% of energy consumption and 36% of CO2 emissions in the EU comes from buildings. As far as new build sector is concerned, we can see there a dramatic fall in energy needed for space heating due to energy efficiency measures in building sector. And this results in an ever-growing share of energy needed to produce hot water. We heat up every day 22 million cubic meters of hot water in the EU homes alone, and yet 80% of this heat ends up in sewers. And with this solution, we are able to recover up to 70% of this wasted energy. Next slide. Here you can see an example from Switzerland, and with gray color you can see energy needed in kilowatt hours per square meter in a year. So gray is heating and hot water is orange, and share of hot water is 50 to 80% of the total energy demand. So in buildings built before 1975, the share of hot water or energy needed for hot water was 10%. Then regulations at cantonal level were strengthened, energy efficiency regulations, and nowadays with the latest Minergie is a green building certification scheme in Switzerland, you can see that we ended up with nearly 3/4 of energy is needed by heating shower water. Next one. So how the system works? We have no moving parts and no electricity required. Of course, there is an exemption, but let's say mostly no electricity. We have a heat exchanger in the system which transfers heat of the wastewater to incoming fresh water and heats up this fresh water from around 10 up to 30 degrees. Why do we use this in showers? First of all, as said, this is the highest consumption of hot water, representing around 80%. Hot water demand and drain water availability go simultaneously and in case of showers. It's a relatively heat exchange. You just need to put these two flows together. And last but not least, wastewater from showers is relatively unpolluted, so ideal for heat exchange. And everything is ready to have 70% of this energy recaptured and reused. Next slide, please. So here you can see the basic principle in a graphic format. On the left-hand side, you can see the first case without heat recovery. Then we install heat recovery and let the fresh incoming water flow through the system. We will heat it up to 30 degrees, and this will result to reduce amount of hot water needed in this mixer mixing tap. This is only one example of the individual systems. We have more systems. When, for example, the preheated water goes to the boiler or storage tank, you will have the presentation and link there to the white paper with more solutions there. Next one, please. Like to show you some product examples. So you can see these are market-ready solutions coming in a box. So you just need, or your plumber just needs to install it. First group of systems is so-called horizontal type, where the heat exchanger is either built in directly into shower tray or in close proximity of this. And you can see in all cases a freshwater inlet and outlet for drain water. This solution here in left side is a solution for pass tube to be connected. Next one. Another type of heat exchangers is vertical pipe heat exchangers, and basically these systems you have to install into your drainage pipe, a fouling pipe, and here you can also see the inlets for for fresh water, outlets for preheated water, and the sewage water is going through the pipe. Next one. Here's some pictures on connection. This is basically quite an easy solution. Plumber has to connect the incoming fresh water here instead of directly to the tap, mixing tap. We go first through the heat exchanger, incoming fresh water, leaving preheated water, and preheated water goes to the tap. In case of vertical pipe, you need to do basically the same. Here is the heat exchanger, and it has to be installed in the drainage pipe and incoming fresh water. For more product information, manufacturers and installation guides, I suggest to visit the WWHR Europe Association's website. Next one, please. Product safety. We are talking here about potable water intended to human consumption. So this is drinking water. That means that we need some safety, product safety rules here. And we have a European standard, EN 1717, about the protection of potable water in case of heat exchanger. And basically, this is ensured by double-walled tubes you can see on the picture. And in case of these double tube heat exchanger, you have a leakage gap here in between two tubes. So it's easy to detect possible leakage. So separation of potable and wastewater is safe and secured. And on a product, you can see fins in case in outer tube, and this is to increase the heat exchanging surface of the tube. That means the efficiency of the heat exchanger. Next one, please. If we talk about efficiency, of course, this depends on many factors, but as a first rule, we can say that the lower the flow rate, the higher the efficiency, and the higher the flow rate, the higher the performance, that means energy you gain from the system. As said, efficiency is basically depends on product itself also, and generally we can say that this product efficiency varies between 40 and 70%. Next one, please. Here we can see a graph of a certain product. First of all, you can see three types of products in the middle of the picture: 3 tube, 5 tube, and 10 tube heat exchanger. Of course, the more tubes you use, the higher the surface and higher the efficiency. So green line is for 3 tube, and this brownish is for 10 tube heat exchanger. And as said, the higher the flow, the higher the performance, and the efficiency, the lower efficiency is higher at lower flow rates. In our example, let's say 6 liters per minute. In case of 10 tube heat exchanger, means around 60% efficiency. Next one, please. Where to use these systems? Single family houses, multi-family houses. Here you have a choice of individual heat exchanger for each shower, or you can also combine more showers, like in this example on a picture. 2 showers are fed by 1 heat exchanger. In case of non-residential premises, we need the ones with higher hot water consumption. That means sports facilities, hairdressers, hotels, swimming pools. And this will be presented by my colleague Hugo in a second part with a swimming pool example. Of course, it's relatively easy installation, so the systems can also be used for renovation of existing buildings. Next one, please. We are talking about market-ready solution, deployable already everywhere in Europe. And Europe has a greatest technological lead in this subject, with over 300 patents applications since 2010, and already over 300 gigawatt hours energy recovered, corresponding to annual hot water consumption of 17,000 households. Next one. So where it is already used, the system is used in countries where the contribution of the systems is acknowledged by national codes or standards. Yeah, for example, in France, system can contribute to targets for heat from renewables. In the Netherlands, recovery system is included in a calculation software for a new construction project, and they contribute to better energy performance of buildings. It's the same in the future for nearly zero energy building houses. And the third example, in the UK, it's also already recognized in building regulations, Part L, as one of the most cost-effective SAP-listed energy efficiency technologies. So highest markets are in countries where the system is recognized in building codes, and savings thanks to this system can contribute to energy performance of buildings. Next one, please. Now let's see an example of a household. Of course, the energy calculations has got many variables. You can see it in this table, starting from shower time up to the number of residents in a home. We used these numbers here, these variables, and the number of residents is, for example, an average European household with 2.3 persons. What we need is for CO2 emissions calculations is coefficient of electricity and gas, how in kilograms per kilowatt hours, you can see it there. And last but not least, very important, that in this calculation we used a market average efficiency unit. I set efficiency from 40 to 70, and we used here a 56% efficiency unit. Next one, please. And here are the results. In the first part, you can see a household without WWHR system. Energy demand per year is more than 2,200 kilowatt hours, resulting into 770 kilograms of CO2 in case of electricity and over 400 in case of gas. If we apply this average efficiency system, here you can see numbers with recovery and here savings. You can see that we avoided 833 kilowatt hours of energy per year, with nearly 300 kilograms of CO2 emissions in case of electricity, and 85 cubic meters of gas, with over 150 kilograms of CO2 emissions. So how much is this? From the original use, it's 37% of energy consumption and CO2 emissions were avoided in this sample. Next one, please. Return on investment. Products price varies depending on system to use. Electricity and natural gas prices really vary across European member states on quite a wide range. So generally, we can say that an average household, an average family can save around 50 to 150 euros annually on their hot water bills. And I really believe that this justifies the investment into this safe and energy efficient system. Next one. Now we go to EU 28 level. Here you can see energy statistics from 2017, and energy for domestic hot water preparation was nearly 500 terawatt hours. Out of this, as you can see in a table below here from the GRC, 80% was used in showers. So 80% of this energy is nearly 400 terawatt hours annually. And this means 14.8% of households' final energy consumption. An interesting number is more than 3% of European final energy consumption goes to shower water. Next one. To calculate the carbon footprint, we need type of fuel used for heating of this shower water. So this is the share of different fuels in 2017, and you can see that gas and electricity accounts for 2/3, 66% of the demand. So let's see how much energy we need from electricity and gas to heat up this water. You can see it here, 264, more than 264 terawatt hours. And let's assume that with an average efficiency unit, we can save 37% of this from the previous calculation. So that means nearly 98 terawatt hours a year can be saved at European level. And what does this mean for CO2 emissions? You can see that CO2 emissions in total amounts to more than 60 million tons a year, and a saving potential using the same 37% is more than 22 million tons a year. Of course, this is a very theoretical potential of each European home. Next one, please. Now we create here a little bit more realistic, but still quite optimistic scenario. We have a renovation-based strategy by European Commission announced in October this year, and the goal by the renovation wave is to renovate 35 million buildings by 2030. Let's assume 82% of these are residential buildings. In this decade, by 2030, we will build 16 million new dwellings in Europe. So in this scenario, let's assume that half of renovated residential and half of newly built dwellings will deploy WWHR systems. So here you can see numbers, number of buildings, 800 kilowatt hours a year can be saved by a household, and this will result to nearly 18 terawatt hours a year, or 1.54 million tons of oil equivalent a year in this scenario. Next slide, please. So, what does it mean in as a contribution to the European targets? In Climate Target Plan 2030, we have a proposal to cut greenhouse gas emissions by at least 55% by 2030 compared to 1990. To achieve this reduction, European buildings should reduce greenhouse gas emission by 60% and their final energy consumption by 14%, and energy consumption for heating and cooling by 18% compared to 2015. This is a target by Renovation Wave. So what does this mean in numbers? Final energy consumption and the greenhouse gas emission in 2015, you can see in a table, and we need 14 and 60% reduction respectively. That means 50 million tons of oil equivalent final energy consumption and 276 million tons of CO2 equivalent reduction by 2030 versus 2015. Next slide. And here you can see the contribution to this Renovation Wave targets by our 2030 WWHR scenario. So 1.54 million tons oil equivalent is 3.07% of the Renovation Wave targets regarding the final energy savings, and over 22 million CO2 savings, million ton CO2 savings equals to more than 8% of the total Renovation Wave target for buildings. Next one, please. Additional benefits of the WWHR system. A hot water preparation system can be designed smaller. That means, in fact, cheaper. We need reduced capacity of installed renewable systems, or energy generated by these systems can be used for other purposes than hot water. These heat exchangers comply with the circular construction targets as long as they have a long lifespan and contain easy to recycle and already highly recycled materials like copper and stainless steel. We have a real-time production here. That means no use, without over or under production. So you use the energy when it's generated. That means no control or no storage system needed. And last but not least, aesthetics systems are integrated or hidden into shower trays or showers or technical rooms, so they are invisible. Next one, please. As you could see from examples of France, Netherlands, and UK, policy recognition of these systems are crucial to foster or to boost the use. First of all, we clearly need a recognition of these systems in an EPBD definition as energy from renewable sources. When it's done, we can use the on-site generated energy by these systems in as a renewable energy in primary energy calculations of buildings in kilowatt hours per square meter per year. So contribution of these systems will be acknowledged to both near zero energy buildings in new build sector or to the existing buildings. In a renovation plan, renovation way, we have legislation tools like building renovation passport for a long-term step-by-step renovation. Minimum energy performance standards for existing buildings. Deep renovation standards or minimum levels of renewables in buildings. In Renewable Energy Directive or EPBD. So we propose to acknowledge or to include, explicitly include WWHR systems into all of these tools and be crucial part of the energy renovation of buildings. Next one, please. In an energy efficient directive, member states shall include the system into their long-term renovation strategy and count the contribution of this system. And in energy labeling, in package label for heating system, to include WWHR a subsystem in the label. That means that next to solar collectors, storage tanks, or controllers, heat shower water recovery can also contribute to the system efficiency of the heating systems. Next one, please. And that's it.
Okay, thank you very much, Robert. Then let's pass on to Hugo, who will present us a case study to illustrate the use of this technology. So Hugo, the floor is yours.
Thank you. So I'm going to present a case study for a swimming pool that is being built in France. The swimming pool has 34 showers, and the engineers and architects had the choice of having multiple individual wastewater heat recovery systems, or having one big system to recover the heat from all the wastewater. And I'm going to present all the calculation they ran for both options and see in the end what they choose. First option, you use single wastewater heat recovery systems for each shower. In this case, what you can do, a small optimization, is you can use one heat exchanger for 2 showers. Sorry, can you go to the next slide, please? Yeah, this is the example of one individual system. That's the O box. And one thing you can see is about 50 centimeters in length and width. And in height, it's about 26 centimeters. Next slide, please. So, yeah, it might scare you a bit. So you can see here, you have one wastewater heat recovery system for shower 1 and 2, one wastewater heat recovery system for shower 3 and 4, and so on. For each 2 showers, you have one heat exchanger. In this case, you preheat the water that goes to the cold inlet of the shower mixer. You do not preheat the water that goes to the water heater, because there are multiple systems and you cannot have the cold water from the water heater go through each of them. And next slide, please. Option 2, you have a single bigger unit of wastewater heat recovery system that recovers the heat from all the wastewater, all the drains. And that's, in this case, it was the O-Box C that was considered. As you can see, it's a much larger unit. It's 60 centimeters wide, and it's 1.9 meters in length. So definitely not the same dimensions. Next slide, please. In this case, if you want to use a single wastewater heat recovery unit, you can only preheat the water that goes to the water heater. Because if you would preheat the water that goes to the cold inlet of shower mixers, you would have too much water above 25 degrees. That would create a risk for Legionella development. So definitely not something we want. So every time you have a single wastewater heat recovery unit, it preheats only the water that goes to the water heater. Next slide, please. So here are the calculations. You have a split for each case of where the energy goes. On the first line in the table, you can see what amount of energy is lost in the pipes, in the air before the wastewater heat recovery system. And what you can see is for a bigger unit, for a single collective unit of wastewater heat recovery, you lose twice as much energy before the heat exchanger because it's further away. You have much more piping. You have usually the unit is a bit far from all the showers in the building. The third line is interesting too, because in locker rooms, because that's the case here, we are in sports facility, it's a swimming pool, you have all the showers at the same time. Let's say you have a class of 30 children going out of the swimming pool. They all go to the shower within 5 to 10 minutes and then nothing. So it's very, very narrow time frame where you have all the showers. And even a big unit as the O-Box C has lower efficiency because it has a great amount of hot water to process. Whereas if you have individual wastewater heat recovery systems, they can handle the flow perfectly. In the end, that's the last line. You see that we recover about 20% more energy with individual wastewater heat recovery systems than with collective wastewater heat recovery systems. And this is where it's interesting. The engineers decided to go with the collective system. And next slide, please. This is because the cost is more interesting in that case. Having 17 wastewater heat recovery systems costs about 10,000 euros just for the hardware. The installation of 17 systems, even optimized, is still costing 6,000 euros. So in the end, the payback time, the return on investment is shorter for a collective system in that case than for individual systems. And keep in mind that having 34 showers is not that much. In most buildings, multifamily housings, hotels, you have 40, 50, 60, 70 showers. or swimming or bathrooms. So usually it's really interesting considering a collective wastewater heat recovery systems in your calculations. And that's the end of the case study.